Have you ever wondered if it's possible to make something as groundbreaking as Super Mario Galaxy's Planetary Gravity run on a Nintendo 64? Well, I've done it, and I'm going to share my code as well. And not just as a proof of concept, it runs at a smooth 60 FPS on real hardware with a trick that can be used in just about any game engine. Let's talk about how I've done it and why my approach might be a bit of a dirty trick. I'm actually not the first person to do this, but I'm the first that I know of to implement this in a way that it's performant enough to run at 60 FPS on a real Nintendo 64. Arthur Tilley has implemented something like this before, but unfortunately it only runs well on emulators. How? By bending the rules of how rendering and physics are usually handled. Here's the funniest part. My planetary physics are actually not even physics. I implemented this entirely in rendering code. Okay, but why? I had to implement this in a unique and really messy way because I wanted to implement this in a way where it would not affect how I process Mario's physics during the entire rest of the game, since that would cost a good bit of performance even when the gravity is not active. And I'm fighting hard for every bit of performance on this hilariously underpowered console that is barely able to handle 3D games. This entire effect is something even simpler than a vertex shader that could be used in just like a vertex shader in about any game engine. Since all that this effect really does is change how the RSP moves around vertices on your screen, this effect is basically free of cost. So let me walk through the math here and you'll see it's actually quite simple. First off, forgive the rough visuals in this unfinished area. It's still a work in progress, but the concept is fully functional. To pull off this effect, we'll hijack the rendering pipeline quite a bit. This video will be a little difficult to understand if you have not watched my render matrix video yet, so I strongly recommend watching that first. With both videos combined, I'm confident that any aspiring programmer can implement my planetary gravity themselves with a little bit of tinkering. While the moon gravity is active, in this level only, the level executes a special rendering function that I'm calling Geo the Moon. This rendering function will handle both the physics and the visuals of this whole planetary gravity setup. Ignore my poor variable names in the 60 FPS interpolation code. I misappropriated random data I had available to me and just reused it for stuff that is not explicitly named for. Anyway, my function here, Geo the Moon, essentially handles all the visual magic for this planetary gravity effect by controlling how the level gets drawn by overwriting and using something called a model matrix. A model matrix is something virtually every 3D engine uses to render models. It's there in Mario 64, and I also know it's there in Unreal Engine 5. How this works is a little complicated, but the basic idea is that a model matrix can move, rotate, and scale 3D models. To that end, these four values here in a matrix are going to be multiplied with the vectors that make up a 3D model's vertex coordinates. And the output of that is going to be the x coordinate at which the vertex gets rendered. The same happens for the y and z coordinates. So for example, by setting this value here to 100 in the model matrix, after looking at the math equations, we can see that now the model will be offset on the z-axis by 100 coordinates. Suffice it to know that a matrix allows for all kinds of math operations that let you scale, rotate, or move, or even distort 3D meshes. The math for this on all known N64 games is implemented at the microcode level, which means it's even cheaper than you'd think. The microcode is something that games upload directly to a special hardware part that renders games on the N64, which means it can run insanely efficiently, although it has to have a relatively low code complexity. Okay, so with all that preamble out of the way, what does the function actually do? First important thing here, it forces Mario to always set at 0, his Y position 0. He's not allowed to move horizontally from the middle of the level. This is not strictly necessary for this to work, but it will make all the following math a lot simpler. Alright, so Mario is physically frozen, but clearly it looks like he's moving. So what is going on? The idea is that instead of Mario moving through space, he rotates the entire level. You can visualize this as Mario standing on top of a gigantic globe. Instead of him walking on the surface, the globe rotates under him when he moves, giving the illusion of movement. Think of Mario Party 1's bumper ball minigame or Mario Galaxy's spinning ball minigame, and how the characters move the ball here. This is done by generating a rotation that represents how much the planet would need to rotate to move Mario from 0y0 to Mario's current position. And then we apply this rotation to the level's rotation. And this level rotation overrides the usual model matrix, but makes the level move around visually. By applying the same matrix to the level's collision, you can have the collision move correspondingly too. Mario 64's engine actually by default comes with support for generating collision off of a matrix, so this step would be trivial. But I figured I can have this be even cheaper by just not doing that, considering how little difference it makes. Since the planet is supposed to be perfectly round in this boss fight, the visual effect is convincing enough without needing to update the collision system, saving even more performance. As you can see, the rotations are handled via quaternions. Quaternions are a really useful mathematical tool for rotations. Unlike simpler methods, like Euler angles, they avoid problems like gimbal lock, which can mess up rotations when working with 3D spaces. And additionally, mathematically, it is super cheap to convert a quaternion rotation into a rotation matrix. Compare, for example, the quaternion to matrix function here with an Euler angle to rotation matrix function. All these trigonometry calls up here are super expensive comparatively speaking. Of course, just Mario being able to move is not nearly the whole thing. Enemies and collectibles need to be able to walk around on our planet, and that will be a much larger challenge. We'll tackle this similarly with a few extra steps. Since now the whole world visually rotates, we need to apply and unapply this world rotations to enemies whenever it is applicable. For this purpose, enemies in this area have a rotation quaternion relative to the no rotation stored in their data. This approach ensures that enemies can move naturally across the planet's surface while still aligning with its curvature, all without expensive calculations. This quaternion decides both where on the planet they are positioned and which way they are facing. It would be possible to add a secondary rotation quaternion to them so that their pitch or roll could be unaligned with the planet's surface, but it really was not necessary in this area. Either way, now that we have the enemy's quaternion, enemies can simply multiply both the world rotation and their own rotation together to find their current rendered rotation and use their unmultiplied rotation to move across the planet. Quaternion multiplication is super simple. You can actually just copy-paste the algorithm off of Google or even ChatGPT if you get lucky, and it's a lot cheaper than a matrix multiplication too, so this is great. Last step is to override the actor's model matrix with our custom matrix, and this is quite hacky, and how this is done is more related to how my render engine works than anything related to how planetary gravity works. If you're implementing this, for example in Unreal Engine 5, you'll want to instead override the getRenderMatrix function. Doing it with a mem copy is just much more optimized way of doing it in my engine. Alright, now that we know how to position our enemy, how can we move them? Instead of moving through space with a forward velocity, they will now move across rotations using a forward rotation quaternion representing their speed. This rotation can easily be generated by getting the vector I'd like my guy to move towards, and then using this quad between vectors function to find which rotation has to happen to get there. This is basically the same thing we did at the start to rotate the planet when Mario moves, except this time it is reversed and the enemy genuinely rotates around the planet. And instead of simply rotating sideways with a facing yaw, they can use their stored rotation quaternion to adjust their forward direction. This quaternion can also be generated somewhat easily with the quaternion from axis angle function. This works because quaternions are incredibly versatile. They allow rotations both around where you are on the planet and around which way you're facing, as shown in this graphic. Moving and rendering like this is very convenient because it's actually cheaper than normal movement. While normal movement wasn't exactly expensive, it's still a neat little thing to know. Unfortunately, we can't just set the model matrix to the rotation matrix like you would with the level. The level had its center at 0, 0, 0 after all, and actors need to move across the world instead of being stuck at 0, 0, 0. So what we have to do here instead is to turn their position into a translation matrix and multiply the translation matrix by the rotation matrix we want to render them with. This multiplied together gets us the desired result. They now render where they should be, can move as they should, and can be interacted with as desired. There are a couple more math tricks we need to, for example, ensure Mario can throw objects forward like this, or that these shockwave the boss produces hit Mario at the right time, but that's more than I want to explain for now. I will attach a code file though that has these examples if you'd like to copy my tricks. Doing it this way also has some camera advantages. I can keep using the camera unmodified and it'll work. If you look at games like Mario Galaxy or Sonic Adventure 2, you'll notice that the camera or the controls sometimes struggles. This is because of the earlier mentioned Harry Ball theorem. It is impossible to have your game controls work continuously and intuitively across a whole sphere like this without turning the camera forcefully, and this has been mathematically proven. I'm sure you've run into some jank because of this if you've played games before that play on a sphere. Now, there are limitations to my approach. If you want to transition Mario between two different planets, you'd have to adjust the math quite a bit to accommodate for that. I'll leave that as an exercise to the listener because it's difficult and I don't need or want to program it. Though admittedly, if you wanted more than one planet, I do not think this approach is a great idea anymore. And you're probably better off programming this whole thing at the physics level instead of the render level. The only real reason I've implemented this at the render level is that I did not want this to impact the physics expenses anywhere else in the game, and it worked well within my plan. Some may argue that this is not real planetary gravity or whatever, but in my opinion, games are all just smokes and mirrors. Nothing you see is real, and at basically every stage of processing, tricks are used to make things cheaper. I apologize if this video was a little hard to follow. If you haven't been able to follow it too well, I recommend checking out the render matrix video I mentioned earlier. Usually I try to make videos about topics closed within themselves, but this concept was rough to explain when assuming no prior knowledge. Shoutouts to all my Patreons for supporting the channel. You guys are the reason I keep making videos. I apologize if my absolute schedule is too sporadic, but I am very busy working on the games that I showcase in my videos, and I'd like to spend more time on my games than I do on my videos. The videos are a lot of work. Speaking of which, Return to Yoshi's Island just got its 15th course finished out of 15. Now it's time to work on the overworld, on some side levels. I'm getting really close to being done with all the content in the game, and then it's more beta testing, and I'm really excited to show you guys what the finished game will look like. Don't expect it anytime soon though. I don't put a deadline. I still need a lot of testing done. Until then, see ya!